We're finally at a point in the semester where we're going to start working with some data to see whereas this supports or not our hypotheses. Today, we're still going to be discussing some conceptual ideas so that we can better understand the statistical test. But the next lecture, we're going to talk about our t-test. And those are going to be the main statistical tests that we'll learn for this class as you move to the second section of this type of course. So this will probably be for many of you in the fall semester. You're going to learn other statistical tests, but the hypothesis testing logic is going to remain very similar to all the other statistical tests that you will be working with. So again, today we're going to cover a little bit more conceptual related things so that we can better understand how we use data to say or see whether it supports our hypothesis or not. Throughout this lecture, I've included some of my handwritten notes because this chapter has a lot of information that can sound very complicated when in reality the ideas are simpler than what you will see in some of the slides. Of course, I want to give you all the technical information because it is important that you are exposed to that information, but also through some of my handnotes, I feel like these ideas are summarized in a way that hopefully it's easier to digest for all of you. So we're gonna start here, and you have access to these notes on, I believe, on your readings folder is where I posted them. And one thing that we've been doing so far is we've been discussing distributions in general. So we've been learning different things about distributions, but I haven't really referred to those distributions in a specific way other than, is it a normal distribution or a skewed distribution? Now, we can have multiple types of distributions, and in reality, the only thing that is going to be changing here is what is that distribution showing you. But everything else that we've learned about distributions applies. It's merely, again, what kind of information is summarizing. So here, what I want to show you, so we're going to start at the top of this. We have our population. Again, your population is going to be absolutely every single individual that fits the criteria for your research question. So again, we kept using this example of if you're doing research on, or your question involves first generation Hispanic students, then every single first generation Hispanic student is going to be part of this population. Again, many times we're not going to have access to the entire population, either because logistically there is no way that we can actually identify every single person that belongs to that population, or because it takes a lot of time and resources and we typically do not have those resources. So instead, what we're going to be doing is getting a sample. So out of that entire population that we have, we're going to recruit a few of those individuals. And again, those individuals are going to be our sample. So again, we talked about how the sample is similar to when you go to an ice cream store, you ask for a sample so that you can get a taste of what the actual ice cream tastes like. And similarly, samples of humans would give us a taste or would allow us to see what the overall population actually is doing, or arguably that is what we're trying to do. When we're working with a sample, the distribution that we speak of is called the sample distribution. So again, in this type of distribution, it's only going to represent that one sample that we collected. So here you can see the orange sample is going to be what is actually shown in the sample distribution. And that sample distribution, again, is going to tell us very similar information in the sense that the x-axis, again, represents a specific score on, whatever is that we're measuring, whereas the y-axis actually represents the frequency. So how many times is that score specifically shown in the distribution? Very similar things to other things we've discussed. The peak of the distribution, it's the mean of the sample. And again, the shape is, or we would read the shape in a very similar way and all that kind of stuff. But in a sample distribution, there are again a couple of things that are very specific to the sample. So in the case of individual scores in the sample distribution, those scores are going to represent an individual. So again, one person within that sample is what we see when we look at individual scores within this distribution. Um, and for us to do this, or for us to find the location of that specific score, we use our C-score formula that we've talked about last time. So again, you hopefully are already very familiar with this. We have a C-score, which is equal to the raw score minus the mean divided by the standard deviation of this distribution. So again, everything that is related to this distribution has to do with one sample, and individual scores represent one individual. And again, for us to find the location of that one person, we use the formula that we have here, which is, again, C-score equals raw score minus the mean divided by the standard deviation. And with that C-score, we would be able to find the location of this one individual and already start making some assumptions of this individual. Is it above the mean? Is it below the mean? Which again already has an implication on how the person is scoring relative to other people within this distribution. So again, we are familiar with all of this. Now we're going to start working with the distribution of sample means. So again, we're still going to read a lot of this information in a very similar way because the format still kind of stays true to what it is. The main difference, though, is that whereas in the sample distribution, we have the scores of individuals that are distributed in this graph, we're going to have now samples. So every sample that you see here is one score. So one score represents one sample. So now if we go back and look at our population, again, we see that we have a sample that is like a circle in purple, another one that's green, another one that's red or pink, I think, and then another one that is orange. All of those samples are represented in this distribution. But what is happening specifically is that I measure the score for each individual in the sample, and then I average those. And then the mean of this sample is what goes into the scores of this distribution. So I don't get each individual information and then that goes here. No, it's going to be the mean of this sample, the mean of the green sample, the mean of the pink sample, and the mean of the orange sample that goes into the distribution. So again, everything how we read the graph is very similar to what we just discussed. The only difference is that previously we were talking about individuals that belong to a sample, and then now we're talking about samples that belong to a population. Other important things to know about this is that because now we're working with multiple samples that are sampling from the population, Then what we're going to see is that when we get the mean of all the means of all the different samples that have collected information from this population, we're going to get a population parameter or the population mean. So we will be able to know what the population mean actually is, because now we're covering more ground of the population. So for instance, you can see here that almost every single individual in the population has been surveyed on the same topic. And again, this was done collectively across multiple samples rather than just one person trying to go into the population and surveying every single individual in the population. So again, now when we're putting together the information across multiple samples, we know even more about the population. So the mean of all sample means is going to equal the population mean. And again, that is still represented by the peak of this distribution. So again, everything that you've learned about the distribution still stays true because we read the distributions very similarly. The y-axis, again, are still representing the frequency. It's just that is it the frequency of people who score at a specific level, or is it the frequency of the samples that have a very specific mean? So now it is a sample versus an individual. And again, we already learned how to calculate a z-score for an individual. Now we're going to be working with getting a z-score for a sample so that we can locate specifically where one of the samples falls in the distribution of sample means. And very similar to how we did with individuals, where the location tells us something about that individual. Well, the location of the sample will tell us something about that sample. Again, is it above or below the population mean? And then what does that mean or imply about the specific sample? Now, this is a formula we haven't worked with yet, but is very, very similar to the one that we have already worked with. We're going to have a z-score of the sample, and it's going to be the mean of the sample minus the population mean divided by the standard error. And again, this is very similar to the other one where we have a raw score minus the mean divided by the standard deviation. We're going to see why in a second we're using the standard error in here. But the formula is very, very similar. We are making a subtraction at the top and then we're dividing by a number in the bottom. Other two important things here before we get into the actual slides. It is important that whatever samples we are including in the distribution of sample means, they have a similar size or they have the same size. And the other thing is that ideally the samples will be larger than 30 individuals so that it approaches a normal distribution according to the central limit theorem. And it has a normal distribution because only when we have a normal distribution, we can use the pieces of information or this little, again, cues that we've learned to use to actually say something about either the individual or the sample. The next slides are going to have information that we have already discussed, so I'm going to go through them very quickly, but again, this is information that we saw on the previous slide. Now, here are some facts about the distribution of sample means. Again, the mean of the distribution of sample means is going to equal the population mean. The main idea is that we have multiple samples that are coming from the same population. So if we add the averages of every single sample and get an overall average, then this is going to be equal to the population mean. The second thing is the larger the sample size, the lower the variability in the distribution of sample means. We've talked about variability before and how is representing how different the scores are to each other, the more information we have, the less variability there is among the scores. And again, this is important because the closer the scores are to the average, the more we can trust our results. So typically we want to have lower variability in our distributions. The third thing is that the standard deviation of the distribution of sample means is going to equal the standard error. This is why in the previous slide, when I was showing you the formulas, we divide by the standard error. When it comes to the distribution of sample means, the standard deviation is actually going to be the standard error. And the standard error is going to be an estimate of sampling error that is determined from the standard deviation of the distribution of sample means. Specifically, it's going to use the population standard deviation and then the sample size for the samples that we're looking at. Now, when it comes to doing any calculations and things like that, I will always give you the standard error. So this kind of formula, rather than you having to learn it, or please learn it or know what it stands for, but when it comes to you calculating it, I will be giving you this information. But do keep in mind that the standard deviation of the distribution of sample means is equivalent to that standard error. Other things that we have already discussed is that we need the distributions to be normally shaped, so that we can use a lot of the information that we have already learned about normal distributions and then how we're going to interpret our data. Now, if the population is normal, then the distribution of sample means is going to be normal. But again, sometimes, because we have no access to the entire population, we will not know what the shape of the distribution is. But according to the central limit theorem, if you have a sample size that is greater than 30, then you're going to approach a normal distribution. So the goal should always be to have samples that are greater than 30. And then this, again, we've also kind of already reviewed on that first slide. So we have two types of Z-scores that we can calculate. We can calculate a Z-score for an individual. So this is what we have done in the past. We found the specific score of an individual, and then we calculate or transform this into a Z-score so that we would know the location of that one individual within the distribution of the sample and compare it to other individuals. Now we're going to be working with the Z-score of a sample. And again, this is what we use in the distribution of sample means, because now we're dealing with samples. So, but the information is very similar and the purpose is very similar. We are transforming it into a Z-score so that it can be standardized and we can make comparisons. And it's also going to give us the location, but now of a sample in the distribution that has information about many other samples. So similarly, we'll be able to make comparisons of this sample to the other samples. Hypothesis testing is going to be a process that we use to test our hypotheses about populations using some of our statistics. One important thing to note is that when we are running statistics, we're typically making comparisons between scores. And just out of chance, we're going to see that the scores are going to be different from each other. So we might be inclined to say that because the scores are different, there is a real difference between these scores, so we provide support for our hypotheses. But this is not necessarily the case. Again, due to chance, we will have different scores between the observations that we are comparing. What we want to know is if the difference is statistically significant. And part of this hypothesis testing is going to be deciding at what point do we say that the difference is statistically significant. Now, we're going to be, again, working with different statistical tests, but for each statistical test, we're going to follow a similar procedure, which again is the hypothesis testing logic. The first step is always going to state a research question and make specific hypotheses. The second step is going to be to set a decision criterion for making decisions about the hypotheses. So again, here's where we're going to decide what kind of difference is going to be considered statistically significant and not just a simple difference that is the outcome of chance. The third step is going to be to collect our data. The fourth step is going to be to calculate our statistics, and we're going to do a little bit of that today. And then the fifth step is going to be making a decision about the hypotheses. So after we've calculated our statistics, we're going to go back to step 2, kind of, and make decisions on whether our statistics are statistically significant or not. So we're starting with the first step, stating our research question and hypotheses, and here we're going to be introducing some new terminology. Now, our research question here is, does memory ability change with age? And the hypothesis is that memory does change with age. Now, again, the terminology that we're introducing here is the scientific or alternate hypothesis and the null hypothesis. Now, the alternate hypothesis is going to make or be the hypothesis that the researcher usually makes, and specifically is going to be a hypothesis where we are predicting an effect. So we're saying that something does actually happen. The null hypothesis, this is something that we don't explicitly state many times. So if you read research articles, you won't see many times the null hypothesis being stated, but it's always there. And it's going to be that an effect or relationship does not exist. So it's kind of the opposite of the alternative hypothesis. The alternative hypothesis says, yes, there is something there and we're going to find it. And the null hypothesis says there is nothing there. Nothing exists. So if we have, again, our research question, does memory ability change with age? An alternative hypothesis is, in the general population, memory abilities change with age. Or it could also be, in the general population, different age groups have different mean memory scores, meaning that there is a difference between them. The null hypothesis would say, in the general population, memory abilities do not change. Or in the general population, different age groups have the same mean memory scores. So again, the null hypothesis is always saying there's nothing there to be seen. The alternate hypothesis will always say there is something there. There is a relationship, there is an effect, there is a difference. Now, here's another new term for us, and this is going to be a two-tail hypothesis. Now, the two-tail hypothesis is going to be when there is an effect that is being predicted, or a relationship, or a difference, but a direction is not being specified. So all we're saying is that, yes, there's going to be something happening, something different, or some kind of difference, but we don't say specifically what the difference is. If we had made a more specific hypothesis, like either one of the ones that we have here, so the first one says, In the general population, older individuals have lower memory scores than younger individuals. So we're saying that again, the older you are, the worse your memory is, right? Because you're going to have older people having worse memory than younger people. Or in the general population, older individuals have higher memory scores than younger individuals. So again, now we're saying that older people have better memory. And again, the thing that I want you to notice here is that not only are we saying that we're going to find something, that there's an effect, there's a relationship, or there's a change, or a difference, excuse me, between different people, but we're also providing a direction of what that finding is going to be. Are they going to have worse memory or are they going to have better memory? If we also provide a direction, a very specific direction, on top of saying that we're going to find something, this is called a one-tail hypothesis. And this is going to be important later on because depending on the type of hypotheses that we have, we're either going to be looking at only one tail of the distribution or both tails in the distribution. So remember that when we have a distribution, we have two tails. We have this tail right here, and we have this tail right here. So if we say that we're looking at one tail, then we have to decide which of these two tails we're looking at. So in the case of saying higher, then we're going to be looking at this tail right here. If we had said lower, then we would be looking at this tail right here. But because it's a one-tail hypothesis, we're only looking at one of them. And as we're going to see right now, whatever extreme scores we are interested in are going to be all located on this one tail. The two-tail hypothesis, because we don't give it any kind of direction, we're forced to look at both tails. So those extreme scores have to be split between both of them. We're going to come back to this later on. But again, it matters whether you have a one-tail hypothesis or not. And again, if you have a two-tail hypothesis, then you're going to be looking at both tails because you have not predicted a direction. You haven't said if it's higher or lower. If you have a one-tail hypothesis, we're going to be looking at one specific tail, like here, because again, you have indicated a very specific direction, in this case, that it is higher, for instance. Now here again, you have my quick notes on this. I think this is an easier way of remembering some of this information. Again, you have the alternative hypothesis, which is always saying that there's going to be an effect. There will be an effect or relationship or difference between groups. So we will find something. The alternative hypothesis can come in two different ways. Either you have a two-tail hypothesis where no specific change is specified, or you can have a one-tail hypothesis where the direction of the change or relationship is specified. Again, you're saying things like it's lower or it's higher. And then you have your null hypothesis, which again will always say that there is no effect at all. There's no relationship, there is no difference between groups. So once we have a clear idea of our research question and our hypothesis, especially if our hypothesis is one tail versus two tail, then we're going to move on to the next step, which is going to be setting our decision criteria. So again, earlier we mentioned that there could be differences in scores simply because of how the data is. And this could just be due to chance and not because there are real differences between the groups if we're making any kind of comparisons. So we have to decide at what point, what type of difference we would consider that is such a significant difference that it cannot be due to chance, that it has to be because the groups that we're comparing are actually different from each other. There's going to be two new terminology that we're introducing here. The first one is the alpha level, and this is going to be the probability level that is used by researchers to indicate the cutoff probability level that allows them to reject the null hypotheses. So again, in a less complicated way, is going to be deciding what percentage of the scores in a distribution are going to be considered extreme. So if we have our distribution, and again, we talked about how the distribution, we have a specific pattern in standard deviations and z-scores, and how the area under the curve is 100%. And we also said that, again, because of our standard deviation, in our z-scores, we have a very specific pattern. So here we have 0, we have 1, 2, oh, sorry, I'm trying, and then 3, and then same thing here, 1, 2, 3, and then these ones are negative. So what we learned earlier is that when it comes to the percentages, again, the area under the curve is 100%. But we also learned that between one standard deviation above and below the mean, which is always at 0, is going to be 64% of the scores. And then we learned that if we also include the scores that are 2 standard deviations above and below, all of this will be about 95% of the scores. So all this area right here is 95% of the scores. And what is left over is going to be this area right here and this area right here, which put together is going to be 5%. So we have 2.5% on this side, and we have approximately 2.5% on this side. And what the alpha level is saying is that this and this are what we consider extreme scores, because they're the farthest away from the mean, which again is always at the middle of the distribution, at the peak of the mountain. They're the farthest away from the mean. They're not represented by the mean very well. So those are scores that we would consider probably belong to a different distribution. So if you get a finding or a score that falls in these regions, then again, it's very likely that that score doesn't belong here and that it truly is different than all the other scores that better fit or are represented by the mean. So let me go ahead and clean this up. So again, the alpha level, what it's doing is telling us what percentage of those 100% scores of all of our observations would be counted as extreme. And then based on that alpha level, we're going to create the critical region, which again is going to be represented by the extreme scores, those areas in the distribution that are considered to be extreme. And depending on whether a score falls in the critical region or not, we're going to either accept or reject the null hypothesis. So here again, you have my written notes that hopefully better show how the alpha level is going to influence the critical region. Again, the alpha level is a decision that we make as researchers about what percentage of scores we will consider extreme. And depending on the alpha level, your critical region is going to be changing because a critical region is going to represent the area in the distribution that has extreme scores. Now here I have 3 different distributions with different alpha levels. So at some point, again, this researcher here decided that their alpha level was 0.01. This 0.01 is 1% of the distribution. So this again is equivalent to 1% of scores. And then right here, what this means is that this tail is going to be 0.5%. And this other tail is going to be 0.5%. Then in the middle one, we have an alpha of 0.05. This is typically what we use as behavioral scientists. And this is equivalent to 5% of the scores. So only 5% of the scores is what we consider extreme. And here we will have 2.5 on this end, and then 2.5 in the other end. And then on the last distribution, we have an alpha of 0.10, which is representing 10% of the scores. So we're saying that 10% of the scores is what we consider extreme. So we have 5% here, and then 5% on the other side. So again, you can see that as the alpha level increases, the critical region also increases. The area that is represented by these extreme scores is going to increase because we go from 1% to 5% to 10% of the scores being labeled as extreme. Now here in the bottom, you also see drawn the null hypothesis, whether we accept or reject the null hypothesis. If it falls in the area that is lined, we're going to accept the null hypothesis. That means that our score is falling within the normal range of scores that are better represented by the mean. If the mean is doing a good job at representing those scores, then it belongs to the same population and there's no real difference. But if it belongs to the areas that we have labeled as extreme, then we're going to reject the null hypothesis because, again, those extreme scores are not represented very well by the mean, and they're more likely to belong to a different distribution. So if it falls on the color areas that you can see, whether that is, I believe, purple, blue, or green, if it falls on those areas, we reject the null hypothesis because whatever statistic we found is so extreme that is most likely belonging to a different distribution, and thus the difference is statistically significant. Now, the other thing I want you to notice here before I move on is that obviously when the area is larger, the critical region, when the critical region is larger, it is easier for us to reject the null hypothesis because more of the scores in the distribution are considered extreme. And actually, one more thing before I move on that is also important. Right now, we're seeing these distributions and the split of the extreme scores across both tails, which would indicate a two-tail hypothesis. But if you had a one-tail hypothesis these percentages here would all be located on the one tail that you decided the effect was on. So here, for instance, I have a distribution, and let's say that I think the score is going to be higher, then we're going to be looking at this tail only. And whatever that extreme score is going to be located on that tail only. So again, whether it's one tail or two tail would decide whether you split the extreme scores into both tails and you're looking at both tails, or if you focus on just one tail and all of your extreme scores are in there. And here we have another visual of some of the things that we talked about. Our third step would be to collect data. In this case, let's suppose that we know the population mean and the standard deviation of a standardized memory test for college students, because many of them have taken it as they've participated in research studies. So again, we are making the assumption that we have population parameters for our college students. Then we might just decide that our study design will involve recruiting a sample of 100 older adults to complete the memory test and then use their mean score on the test to compare to the young people. Our sample of older adults represent the population of all older adults, so anyone that's over the age of. So we would then do some calculations. In this case, we would use the formula for calculating the Z-score of a sample, again, because we are working with two different samples. The one which is the population of college students, so these are the ones that we have information for every single individual, and then we have a sample of older adults. And what we want to see is if the sample of older adults belong to the distribution of college students. If it belongs to that distribution, then we would say that they have similar memory. If we find that the sample of older adults land on the extremes of that distribution, then we would say that older adults belong to a different distribution, and thus there are real differences between them. But again, for us to be able to make comparisons between two different groups, we have to standardize the information so that we can see, again, where the sample that could be from another distribution is located within the distribution that we are familiar with, which is the one of college students. So here again, we are calculating that Z-score. And again, this is a Z-score for a sample. And all we're doing here is plugging in the information from our data into the formula that we discussed. So here we have the population mean, which is what you see right here. And then here we have the sample mean, which is what we see right here. So again, in the top, very similar to what we've done in the past, we are going to be subtracting this number so that we know what the distance is between this sample mean and the other one. In the bottom, we have our standard error. And again, our standard error is assuming that we have information from the population. In this case, again, that is exactly the assumption that we made, that we have this information. So we have a standard deviation of 20 for the sample. We'll get back to this later. And then the sample size, which is 100 in this case, because we recruited 100 older adults. So once everything is plugged in, all you're going to do is do the calculation. And here we get a Z-score of +9. Now, last time when we were working with Z-scores, we talked about the table that would let us know what are the number of scores that are represented within a specific Z-score. Now that table, or a chunk of the table, is right here. And we can see that the Z-score we have here is a Z-score of 3.51. And with this Z-score already, we have 99.9% of the scores represented by that. So this number right here is way bigger than this Z-score right here, which is already telling us that is going to absolutely be part of the extreme scores. Now, typically, when we calculate statistics, they're going to come along with a p-value. And the p-value is going to be a probability value that is associated with an inferential test that indicates the likelihood of obtaining the data in a study when the null hypothesis is true. It's going to also be a reflection of our alpha level. So depending on what alpha level you decide, your p-value is going to match that. Again, typically for social sciences, the value that we get is 0.05. So 5% of the scores are considered to be extreme. But the alpha level again can be 0.01 or 0.10. So 1% or 10% of the scores to be considered as extreme. The p-value would follow that lead. So if you, as a researcher, made the choice that the alpha level is 0.05, which again is very typical in social sciences, then all your decisions will be based on whether the p-value is greater or smaller than 0.05. But if you choose that your alpha level is 0.10, then your decisions will be based on whether the p-value is smaller or greater than 0.10. Again, because as social scientists, we typically use 0.05, we'll continue working with 0.05. So here again, we have, or I have my written notes in here, and I've wrote down whether you would be happy or sad as a researcher if you have a p-value that is greater or smaller than 0.05. But this is going to depend on the type of hypothesis that you are predicting. If you are predicting the alternate hypothesis, which says that you will have an effect, there is a relationship or there is a difference between groups, and you get a p-value that is greater than 0.05, you're going to fail to reject the null hypothesis. And you're going to reject the alternate, meaning that, again, you found no support for your hypothesis. If you find that the p-value is less than 0.05, then you're going to be very happy because you've rejected the null hypothesis and you've accepted the alternate, which is typically what you are predicting. But there will be some cases when researchers are predicting the null hypothesis, and the null hypothesis says that you will find nothing. If that is the case, then getting a p-value that's greater than 0.05 is going to make you happy because we are going to fail to reject the null hypothesis because our, again, findings did not support that. But if you get a p-value that is less than 0.05, then you would be really sad because that means that you have rejected the null hypothesis when you were hoping to not reject the null hypothesis. Now, again, many times we don't have information about the population. It's actually rare that we have information about the population. For us to calculate that Z-score of the sample and do the Z-test, so what we did previously is called the Z-test, we need to know the population parameters. When we don't have those, what we have to do instead is use a sample to estimate the parameters of the population. And when this happens, we're no longer going to do a Z-test, we're going to be using a t-test. It's a very, very, very similar statistic. The only difference is that the C-test uses population parameters, whereas the T-test is going to use sample parameters. And that's exactly what we're going to be doing on the next class. Last step is to consider our statistics after we've made these comparisons, and then go back to our step 2 and see what we decide would be considered significant or not. And based on what I said 2 slides before, depending on that p-value, you would be able to make that decision. If it's less than 0.05 and you're predicting the alternate, then you would be happy because you have been able to reject the null hypothesis. And the opposite case if you find the opposite. Now, it is important to keep in mind that data is not perfect, and sometimes we can make mistakes. And specifically, not necessarily that miscalculated something, just simply that it's not as representative of what we think it was. Now, there's 2 specific type of errors that you can make. Type 1 error is when a hypothesis test says that we need to reject the null hypothesis when in reality it was true. So again, the null hypothesis is saying that there's nothing going on, and we say, based on our statistics, that there is something going on when in reality there was nothing happening there. Type 2 error is going to be the opposite of this. We're going to be saying that we failed to reject the null hypothesis when in reality it was actually false. So again, we're saying that we found nothing when in reality there was something going on in there. So again, type 1 error and type 2 error are going to be the type of errors that we can make when we are deciding if we have significant or not significant results, which consequently mean that they are differences or no differences, there is an effect or no effect, or there's a relationship or no relationship. Some of these errors are also related to your alpha level because, again, as we saw when we talked about the critical regions, the larger the alpha level, the easier is going to be to reject the null hypothesis. So we would increase the likelihood of doing type 1 error if we increase our alpha levels, or we're more likely to do type 2 error if we decrease our alpha levels because those critical regions become smaller. Now, power here is the ability of a hypothesis test to detect an effective relationship when one exists. So again, it's going to give us an indication of how much power we have to actually be able to answer a research question. Here's a table. If you're more visual kind of person, this might be better for you to understand the difference between type 1 and type 2 error. And here you have, again, my written notes on type 1 error and type 2 error, as well as power, in case that, again, this is easier for you to understand than how things are written in more technical terms. So I mentioned a little bit earlier that there will be some instances when we will predict the null hypothesis. Now, it's not very typical because we're often predicting, again, that there's going to be a change, there's going to be a relationship, there is a difference, but there are some instances when what we actually are expecting to see is that nothing happens. And this is very important, for instance, in when we're testing the effectiveness of psychological assessments. Because we want to make sure, for instance, that these instruments are measuring things accurately across various groups, right? So we would want, for instance, that a psychological assessment on intelligence measures or is just as accurate in measuring women's intelligence as it is men's intelligence. And in those cases, again, we would predict or hope for the null hypothesis because we would want to see that there are no significant differences in how the measure is assessing intelligence. So there will be some cases where, again, the null hypothesis is exactly what we are predicting or hoping for. And the last thing that I'll leave you with is statistical significance. So again, we kind of started the conversation by saying differences will always be there. Just by the fact that data is not perfect, you will have differences happening when you're comparing groups because of chance. But is that difference statistically significant? And again, when we are in step 2, deciding the alpha level and the critical regions and all that kind of stuff, we are putting some kind of measure into what is that we consider statistically significant or not. So it's not going to be just any difference, it's how large the difference is going to be. But even then, when we have a statistical significance test, it doesn't mean that it is important. There are many things that if we have a large enough sample, we'll find significant findings. But the thing is that it's not necessarily going to indicate something that we're interested in. So for instance, it might be a significant relationship that tall people in comparison to short people love the color blue. It could be statistically significant that, again, this difference is big, but it doesn't mean that because it is statistically significant, I can do something with those findings to change your life and the life of other people. So sometimes we'll have things that are statistically significant, but not practically significant. And what we want with our research is that they are statistically significant if we're not predicting the null, which again, there are some cases where we are predicting that, and that they are practically significant. That again, I can use this new information to do something that is going to improve your life and the life of others.